Welcome to lecture 8, transformation law for Cartesian components of a tensor. So we've done transformation laws for Cartesian components of vectors. So this time we're going to be talking of a tensor, and we'll try to express it with respect to different Cartesian different components basically. So let's start with this. If you have Tij, I guess one expression you've seen a couple of times, right? So this is a component of T, which is a tensor. This is the how do I say, the basis. We can see this is like it's a vector, right? This is a vector on the basics which you're using to describe it, and this is a transformed one. If you remember, product of T and EJ will give you a transformed vector, right? Yeah. So this is a transformed basis, basically. So Tij, then you have Tij prime is equals to this prime, Tej prime. So this one is with respect to Ei, and this is with respect to Ei prime. So this is just trying to tell us that we are trying to express the components of a tensor with respect to different bases or different coordinate systems. The tensor itself will not change, but its components will change. That's basically what happens. So if you look at this, then Eij, if you can remember this expression, TIEM, right? Rotation tensor is a matrix, this one. And if you apply that to an original matrix, or to original vector, sorry, the vector changes, right? It becomes rotated, changes. We're going to be substituting this into, this is star 1, star 2. So you're going to be putting star 2 into star 1, right? So we get Tij prime equals to QMIEM, right here, dot TEJ prime, right? Now, if you also look at this TEJ prime can be represented with its, you can change this to QMIEM dot TQNJEN. I guess you can see what's happening. This EJ, it's similar to what is we have in this Q star here. This Q star, but we just simply used QNJEN. Yeah, making sure we don't use the same, not to confuse everything up, right? Yeah, I hope that's clear. Because if you look at this closely, if you look at this, if we sum on the ends, it vanishes, right? We have a J here. Here we have sum on the M's, we have an I here, we give you IJ. And here we have an IG. So what's on the left will still remain will still be equal to what's on the right. You can pause the video if you think I probably went too fast, but basically this is not anything different from what we've done before. So I'm just only substituting, putting star 2 into star 1, and this QIJ, I found an expression that makes it for the substitution as well too, right? So QIJ prime is equals to QMI. We bring out this other Q because they are rotation tensors, then EM dot TEN, right? TIJ prime is equal to QMI QMG TMN. This has become this. I guess that's straightforward and easy to understand how that happened, right? Because if you look at this expression, where is that? If you look at this expression, if you look at this expression, it's similar to that. If you look at this expression, is similar to that. So you can just pause the video and take a look at it closely. All we've just done is that we avoided using the same letters we've used before, right? Yeah. So so basically, in matrix notation, this equals to Q rotated, right? Not transpose, sorry, times let's bring T this way, let's bring Q this way. Does that look clear? Right. So T equals to Q, it's still the same as this. Q T prime and Q T. Okay. So Tij is equals to Qim Qgn T prime Mn. Now compare these two expressions, compare them, and see what has happened in these two, in between these two. So T and T prime are different. It's clear, right? They are different matrices of the same tensor. Different matrices of the same tensor. The matrix itself does not change, but its components have changed because they've been acted upon by these terms Q. These Q's, they seem to rotate them. They cause a rotation that changes the component, but the matrix itself does not change. Okay, now let's solve an example. Let me look for an example that will probably... Okay, so if we have x1, x2, let's assume the x3. We are rotating about x3 this time, right? So a1, we have e2 here. We have e2 here, and we also have e1 prime here. Then we have e2 prime here. Now, what does this tell us? If you see e1, if you move counterclockwise, you get e1 prime, that's 90 degrees. e2, if you move counterclockwise, you get 90 degrees. So what is this? From this question, it's already obvious that ei prime, so let me write neatly, ei prime is rotated, it's ei prime is obtained by rotating ei by 90 degrees. Okay, sorry. Let me use mathematical term. By rotating ei about e3 through 90 degrees. So e3 is somewhere here. E3 is somewhere here, right? If you rotate about e3, you still get e3 equals to e prime, right? But we get a new e1 prime and e2 prime by moving 90 degrees counterclockwise. 90 degrees counterclockwise. I trust this makes sense, right? So we have a tensor T. We have a tensor T, right? And T, the components of T are given as 0, 1, 0, 1, 2, 0, 0, 0, 1. And this T is with respect to EI. Question says find T, but this time with respect to EI prime. Okay. let me just make things straightforward for you. We have a t, right? And we have a t with respect to ei and a t with respect to ei prime, rotated by q, obviously. So we have this already. We have to find this, right? And we can find the q from we can find the q from the information we've been given, because we've been told already that e1, that ei prime is obtained by rotating e1 about ei about e3 through 90 degrees, 90 degrees counterclockwise, right? So it's very straightforward to obtain our q, right? If for us to obtain our q based on the previous example, if you can remember closely, you see, q will be 0 1 0 minus 1 0 0 0 0 1, right? If you look at this from e1 prime, e2 prime, e3 prime. I love going through stuff again to make things clear. Okay, so e1 rotated to 90 degrees to become e2, right? So e1 prime is now equal to e2. That's why we have just one value in e2. Then e2 prime, which is this column, is now equal to negative e1, which is just only this, another part of 0. Then e3, when we rotate about the same axis, you still get, it's still e3. So all is e1 and e2 are zeros on this. So we've gotten a q. That's basically like what we did in second example. Now this time we need to find t prime, right? This is t prime is the matrix itself, and t, e, I are the components, right? Okay, so how do we go about this? It's very simple. So t is equal to q prime t q. We've given this expression previously, so if you look up closely, you see exactly how we come about this, right? So if you write these terms out, transpose actually, not prime, it's true that you don't transpose, right? We're getting 2 minus 1 0 minus 1 0 0 0 0 1. You can use your calculator to calculate this, or if you want to see how smart you are, you can expand that out. I hope this makes a lot of sense. So this is t, this is t with respect to ei prime. So if you look at them closely, this is your t, this is t, this is t prime, right? These are just the components. These are the components. The components itself have changed, but the matrix itself does not change, right? Exactly. I'm sure if you find the determinant of them, it should be equal. Well, I'm not sure about that. Let me not talk about that yet. But like the other one, when we found for the vectors, the magnitudes were the same of a, magnitudes of a and a prime were the same, right? What I'm sure of exactly, I'll tell you what exactly is the same about the components. Okay, then some extra notes. So for t and t prime, tii is invariant. tii, if your guess is as good as mine, we've looked at this before, it's this, right? Which is called trace. If you look at the, okay, yeah, right, okay, that was what I was trying to think about. The trace of the component of the different components are the same. If you look at this, 0 plus 2 plus 1 is 3. 2 plus 0 plus 1 is 3. So the trace is the same. So the trace does not change. So the trace doesn't change despite the transformation. I hope that's clear. Yeah, you can confirm this and try on different types of angles and see. That should make things clear. Okay. If you have, let's say something alpha, right? If you remember what you learned before, this is a scalar, or is still called a zeroth order tensor, right? AI prime is there, then equals to QMI a dot. Matrix times a vector, we give another vector. A rotation tensor rotating a vector, we give another rotated vector. The magnitude does not change. That's the length does not change on the vectors, but the orientation has changed. The angles have changed, right? So this is a vector, what they call first order tensor. Tij prime equals to Qmn Qnj Tmn, right? I mean, if you look at the orders closely, if you sum all the m's, you remove. I mean, if you sum mj, these two mj, right? Then this will be mn. Sum all the m's, you have gn, right? What am I doing? Am I up? Okay, yeah. So let me see. Well, anyways, if you did for you to transform a tensor to another tensor, right? You have to act. It must act on two rotation tensors. One is being transposed. Yeah, I think that's where. Yeah, one is transposed. So you get this time you get a tensor or a second order tensor, right? Then if you have Tijk prime equals to Qmi Qng Qik Tmnr, right? You get a third order tensor. Can you notice something? As you so for you to the number of Q terms, right, the Q matrices increases as the order increases, right? So for you to rotate a third order tensor to another, I mean to rotate one tensor to the other third order, you have to multiply by Q by the number of orthogonal matrices. So if you want to move from one vector to another vector, just one, two from a tensor multiply by two, third order, three to nth order. How that makes things pretty straightforward and clear as well too. So another thing is, I mean, basic addition rule should work or it should hold, right? Remember Tij and Sij, these are simply components of a tensor. Components of tensors, right? Tensors T, tensors S. So if you do this and do this, that's fine. When you add them together, what will give you another, maybe let's say Aij, right? And AI, which are still the components of a tensor. This is second order. Makes sense? Tijk plus Sijk Aijk, which should be, I guess, as good as my third order. Then for the multiplication rule, AI, they are components of a vector. Tij is components of a tensor, right? So AI is a scalar. AI, AJ, AK are components of a third order tensor. Make sense? Then Tij, Tkl will be the components of a fourth order tensor. Right? For the quotient rule, so AI components of a vector, Tij components of a tensor, right? Then we can get this AI equals to Tij Bj. You sum on the j's and get an I, right? So Bj will be the component of the vector. So I mean, this is basically what you're already used to. Tij is like a transformation, transform this vector to another vector, right? Yeah. But if Tij is not Q in this case, Q will transform it without changing anything. But this will be, Bj will clearly change from Aj. The length will be different. But if it's a Q, the length will remain the same. Yeah. Then if you go further and think in continuum mechanics or mechanics of solid problems, right? Or even some finite element problems, you see an expression like this. It's a very common expression. This is second order, this is a fourth order, this is second order, right? Yeah, so you see this is, I think it's called stress-strain relationship. It's like, I mean, look at your, what's it called? Yeah, stress-strain relationship. Or is it Hooke's law? Yeah, stress-strain relationship. So another very important thing is symmetric and anti-symmetric tensors. Now, if you have a tensor like this, these are the components, right? If the components, or yeah, this is a matrix itself. Yeah, the components there. So if, okay, let me write it this form. If you have a matrix T and its transpose is equal to itself, then it's a symmetric matrix, right? Same thing with the tensor, it's symmetric if its transpose is equal to itself. So if Tij is equal to Tij phi equals to Tji, it's symmetric. What that means is like T, for instance, 1, 2 is equal to 2, 1 is equal to T1, 3 equals to T3, 1. It's still equal to T2, 3 equals to T3, 2. These are all proper. This all shows that the matrix is symmetric, right? For an anti-symmetric matrix, let's say your T is equal to negative TT, then we call this anti-symmetric. What this means is that if you have the matrix for terms, right, one term is not exactly equal to each other. It must be followed by a negative sign. What that means is Tij is equal to negative Tijt equals to negative Tji. Just switched. Note the difference between this 3 star 4. Star 3 and star 4. Note the differences, right? What this means is that T11 and T equals to T22 and equals to T33 is equal to 0. The diagonals of an anti-symmetric tensor is 0. Then T12 is equal to negative T21. T13 is equal to negative T31, right? And T23 is equal to negative T32. I hope that's kind of explicit to understand, right? A numerical example will sort of clear things up, but know that the symmetric matrix we have, first of all, for every T we have 9 terms, right? 9 terms. For the 9 terms, for this one, 9 terms, but for the symmetric matrix, for the symmetric matrix, T12 and T21 are equal, 13 and 31 are equal, T23 and T32 are equal. For the anti-symmetric matrix, it's not the same. There must be a negative sign in between. Then for the symmetric matrix, the diagonals have values. But for the anti-symmetric, the diagonals are all equal to 0. Now, every tensor, this is very important to know, every tensor can be decomposed into symmetric and anti-symmetric parts. So T is equal to T of S, not TA, where this S here means symmetric, this A means anti-symmetric. Does that make sense? Right. So Now to find, how do you find the symmetric component or symmetric parts? T of S is equal to take the original one T plus T of its transpose divided by 2. To find the anti-symmetric parts, you simply take the original one minus this time this divided by 2. Is that clear? That's how I'll give an numeric example for the end of that. Then another thing to note is this: if you find, you can the trace, right? Let's call trace TR. The trace of the product of symmetric matrix and let's say W is anti-symmetric, right? Is equal to 0. What this means is a symmetric W anti-symmetric. So if you find the product of SW, right, and you find the trace, which is the sum of diagonal entries, you're guaranteed to get 0 at the end, right? So if you look at the trace of that, is still equal to the trace of its transpose equal to the trace equal to WTST. These are just expressions you have to know. Okay. Yeah, okay, right. Let me give an example. Now if we have T, let's say T is equal to, let me think of something, 1 4 1 2 3 2, let's make things easy, 1 1. Okay, right, that is T. To find the symmetric part, what do? We simply say T as T equals to T, the original one, plus its transpose over 2, right, equal to 1 4 1 2 3 2 1 1 1 plus its transpose, which is 1 2 3 4 1 2 1 1 1. Diagonal entries do not change, right? Divided by 2. If we do this correctly, let's see how this is going to evolve. 1 plus 1 2 plus 1 6 3 2 3 2 1 2 1 1. Cross check this and I hope you should get exactly what I've just gotten, right? Then for the anti-symmetric part, right, get TA equals to the original matrix, no, minus its transpose this time, right, all over 2, right? Okay, equal to, if you look at, you can just, okay, instead of, let's, to save time, so yeah, it's basically the same thing, but the difference is that we have a negative in here, the middle, right? So if this is done correctly, it should be 1 minus 1 0 minus 1 1 1 0 0 minus 1 0 0. So that is the T of A, right? I hope this is clear enough. I hope that's kind of easy to follow. Okay. So yeah, if we look at this, where is this marker? Look at the terms in this, the diagonals, they're all zeros, right? If you remember what we said about the antisymmetric part, where is that? If you remember, this of it is 0, and that's what we just got in there. Now if you look at this one, this is T of A, right? T of A, look at this term, look at this. This is T21, T12, right? Look at this term, look at the terms, they are simply the same. Look at this. I mean, if you try this for any matrix, it works, right? For the anti-symmetric part, look at this. This is 1 minus 1, T2 1, and T1 2. The only difference is that the one has a negative sign, right? This one's they are zeros. So if you try this, and it's guaranteed that's going to work that way, right? So for the anti-symmetric matrix, okay. For the anti-symmetric part of the matrix, basically, it has three independent terms. Why? Because you look at T12, it's just a negative of T12. It's T12, right? Or T21, sorry. Yeah. T13 is just negative of T31. T23 is just negative of T32, right? So it has three components, or three, these are like three components. And if you remember, a vector has three components also, right? Good. So look at this. For every anti-symmetric tensor, let's call it W, there is a corresponding vector T of A such that for every vector A, the transformed vector TA can be obtained from the cross product of TA with A. So I've written a lot of grammar there, but just this is like a summary, right? So for every antisymmetric tensor, there is a corresponding vector which is called T of A. For everyone, there is a corresponding antisymmetric vector, right? A corresponding vector which is called a dual vector, which is called T of A. So this is the dual vector. So for every antisymmetric tensor W, there's a corresponding vector, and so that for every vector A, the transformed vector, this is transformed one here, transformed vector can be obtained. So for you to find the transformed vector, if you can find this dual product, you can get it, and you find the cross product of that with the original vector, you're able to find the transformed vector. And this dual vector will come from the antisymmetric vector, the antisymmetric part or tensor itself, right? This might be a lot to take, but I hope I'll write expressions that will make things easy for you to understand, right? So for T12, you go to E. We are already familiar with this expression, right? Already, and this can be expressed as this dot product of TA times E2, right? E1 doesn't change. You see, all we've done is this. See this expression T2 we're replacing all this by this, right? So that's why you see this E1 is this one, but TE2 becomes this, right? So it's equal to T of A dot E2 times E dot cross E1. Understand? We simply rearrange the expression. E2 cross E1 will give a negative, so it'll be TA dot E3, right? Equals to this. You can write this expression this way. That's it. So that is T12. T31 is equal to, I'll just write this very fast, but you can copy it, and if you pause and understand, you discover that it's exactly the same thing I've explained the first expression I've just written. E1 cross E3, so negative TA dot E2. which is still negative 2a. Yes. And 2, 3. Now let me do this last one. The other one, C3 equals to E2 dot TA cross E3 equals to TA E3 cross E2. We introduce a negative sign. Plus T1 E dot E1 equals to negative T1A. Right, I think similarly, T21 equals to T3A, T13 equals to T2A, T32 equals to T1A. Right, now if you look at these expressions very closely, you can see the pattern already. We have 2, 1, 3, we have a 3. If you have, we have 1, 2, and 3. So if you don't have any of them here, you know that the dual vector will be on that one. See, 3, 2, 1, right. That's kind of straightforward. But for these ones that had to see it, so that's a mistake. We see 2, 3, 3, 1, 2, 3, 3, 1. They had negatives in front of them. See, but these ones had positives, right? 1, 3, 2, 1, 2, 3. If you can remember from what we looked at, if you remember the expressions, you'll be able to see clearly a pattern evaluating. I encourage you to write them out as I've explained, and slowly you begin to understand what has happened. Then if you look at the values of T11, T22, and T33, they are equal to, guess, well, that's zero straight away. And I hope that makes things clear. So the dual vector TA, this is the expression you need to, let's say, memorize or understand. 2, 3, E1 plus T31 E2 plus 2 1 2 E3 brackets, right, is still equal to T32 E1. That will flip it, take away the minus 1 3 E2 plus T21 E3, right, or 2T A equals to EI. This simply, no, the expressions you need to see. So this expression, that's one, isn't that one? 1, 2, 3. I hope the concept of the dual vector becomes clear, always clear to you. For every anti-symmetric tensor, there's a dual vector. And if you look at the expressions 1 and 2, the difference is simply the fact that the negative sign has been removed, so there's a flip, right? If you see 2, 3 became 3, 2, or 3, 1 became 1, 3, T1, 3, right? And that's what. Then this number 3 is the expression in this indical notation, right? Yeah, I know sometimes this could be a lot to take, but I hope you're able to understand clearly what has just happened. Okay, now if you look, I would like you to scroll back and check the previous example. That'll be all the way up. I don't want to start scrolling through up due to sorry, I mean it might be a bit difficult for you to follow, but if you pause the video and take a look and see what had happened in the previous example, I want to find the dual vector in that example, right? Good. So if you just follow this expression, negative 3 to 3a e1 plus t31a e2 plus t1 to a e3, right? Just simply negative e1, negative e2, negative e3 to give you e2 plus e3. Now you may ask, how did we get this? If you look at the expression for t2 3 plus, this one to e1, you get 0, T3 1 you get a 1, and T12 you get 1. If you look at the expression, just scroll up a little, you'll be able to find that and you get this. Then another question that can emanate from that is like verify TA equals to TA times A. This is the dual vector, don't forget, dual vector. A is the vector transformed, this is transformed vector, right? Because if you multiply a tensor by A, you're transforming it, right? So if you look at that, T of A, from what we're quoting on top, is A2 plus A3. The original vector A itself was E1 plus E3 from the last example. So if you find the cross product of both of them, that will be negative. The cross product of TA times A will be negative E3 plus E1 plus E2, which is equal to B, right? Well, let me just scroll up so you don't. Yeah, so this is T. This is the T, right? You can pause the video and take a look. You will see, you will get what we are driving at. But anyway, I will explain in the next, tutorial session, this example on how to verify this. But two things you need to know is the fact that some things you need to know basically, like every tensor has a symmetric part and an anti-symmetric part, right? Then for this anti-symmetric part, there's a dual vector to it, and the cross product of that dual vector with this vector will give you the transformed one. This is an expression you need to verify. So verify these two for every for every tensor, sorry. Yeah, I don't want to make this very long. I hope this satisfies your curiosity about understanding tensor analysis. In subsequent videos, in tutorial session, I'll solve some problems, I'll put things more in perspective and explain more. Thanks for your time.